Welcome to another very exciting session of healthcare entrepreneurship. So, today we are going to talk about where we left in the last class and go from there. Okay. So, let us get started. This is one of the most common 3D printing techniques which you will come across. So, within the fused deposition modeling or this FDM 3D printers, if you look them up or try to buy one from let us say one of the online stores or any other particular store, you will see n number of these kind of printers. By n I mean like almost infinite, right? Like there are close to 500 to 1000 different printers which are currently available in the market. They come in different custom shapes and sizes from different brands and majorly from very unbranded startups, fairly popular in India, right. So, in the Indian scenario you will majorly get printers anywhere from the cost of let us say 10,000 rupees 3D printers which you can just take for your house and try a few things out, or if you are an entrepreneur trying to build something, so you can take it for your office and whatnot, ranging from there to as high as like 50 or 60 lakhs or even going to crores, right. So, that is the range of things. So, what are the key aspects here? How is a printer costly, or how is a printer different from another printer? So, we will have to analyze few things here in terms of the different categories of the FDM printers. So, FDM, as I have told, is the broad category which you will see widely in the market. Usually in the foreign countries it is much more specifically about in the US and Europe markets, you will see much lesser versions of this and variants of this. In Indian market you see a lot, and one of the key reasons for that is majority of these items used to be Chinese, right. So, basically you would buy a lot of these Chinese DIY kind of printers. They will come to you for 4,000-5,000 rupees, even less if you buy in wholesale. So, it comes with all the parts, and then typically lots of companies, this I am talking about 10 years, the past 10 years, and things have not been looking very well in the last 3 or 4 years for these companies, but majorly what these companies are doing is they buy parts in bulks and they print, they basically use their DIY or their technology, they have the technology know-how, and they build these printers in their own shop and sell them for a much higher price. So, let us say they buy the parts for 2,000 rupees and they are selling it for let us say 2 lakh rupees, right, this particular set of printers. That much amount of variation may not be there, so maybe 2,000 for 20,000. So, they are still making 8 to 10 times profit, right. So, what are the typical 3D printer variants? Let's take a look. So, the first one is depending on the make. Is it a commercial grade 3D printer which you are looking at, or is it a general and DIY printer? So, a lot of these DIY printers are also available for all of us. You just look on Amazon and search 3D printer, you will see majority are DIY kind of printers. That means it will come with this 300 or 500 parts to your home. It will be delivered, and there will be a manual and maybe some accompanying video through which you can watch that or go through the manual and slowly build up with the parts. There are several mechanical components, electronic components, there are motors and several other wirings and stuff like that, and it is nice to build, like if you have some engineering know-how or hands-on, you can build them. So, whether the make is commercial, general or DIY, this makes a lot of difference, right. Second is built area. So, what is the built area are you looking at? Are you looking to print your product which is this small, this big, that big? What exactly is your product size? If your product size is let us say 50 by 50 millimeters, like which is 5 by 5 centimeters each, centimeter square, you are typically looking at a printer which is of the built area of 10 by 10. You do not want to buy a printer of 5 by 5, that is too small, that is just kind of pushing to the edge. No, we do not want to do that, right. We want to have the printer a little bigger than our need of the particular product which we are trying to print. So, built area can vary very surprisingly from micro levels to as big as 2 meters by 2 meters, which is almost as big as a human size, right, or little bigger than a human size, the highest height of humans like which you can see. So these are some of the sizes which are available across the globe, right. Micro printers are sometimes used for making very small nanocircuits, microcircuits and these kind of things, very detailed biosensors and stuff like that. Generic printers of the size 220 by 220 mm, like which is 22 centimeters, is very common. Then you have 500 by 500 mm, which is half a meter. Then 1 meter is much less common. So the more you go higher on size or lower on size, it's much less common, right. The more generic ones are this 250 by 250 or half a meter by half a meter. These are the generic printer volume sizes, right. So having said that, let's take a look at few of these printers. So the first printer here is a very different type, where you are basically seeing it is printing an insole, set a pair of insoles, like this is the first figure on the group of figures, and this is printing it layer by layer, and the base looks like it is completely fixed. So basically the entire assembly of the feeder and the extruder is moving around in all the 3 axes, right. This is what I would think from this. The next printer is a little smaller in the build size. So the plate which you are looking at is basically defining the build size. So if the plate is typically of the size 250 by 250, which is 25 centimeters by 25 centimeters, the usable area is you could subtract typically like 2.5 to 2.5 centimeters each, like on each of the sides, right. 2.5 to 3 centimeters to be very safe. So you are looking at a 220 by 220, almost like of a built area. Then almost the same is repeated along the height. So if you have a 25 by 25 centimeters built area, then the height available is also typically 25 centimeters. There are several printers which have longer heights because they are trying to build something like this, like pillars or poles. So those can behave a little differently or have different sizes, right. Another example of the third printer is where they are trying to print 3D face shield, these basically the visors or the different parts which you wear along the head, and they are trying to stack several models along with it. This is typically a Prusa printer. Prusa is a brand which has several outcomes like that. The fourth picture, which is on the right bottom, is typically a type of printer which has a little bit different movement for the extruder. That single extruder has a very long like reach for the depth or the height. So as you can see, the height is much larger than the area which is available. So these kind of printers are also there, which are building the poles or making several structures which have to be tested for different purposes, right. And then you have the women sitting in this BLB kind of printer. This is one of the largest size printers around the world. There could be a few bigger ones which are used to build automotive car components as well as shipbuilding. Ship cannot be built with a 3D printer typically, but there are certain printers which are building the prototypes of those ships and technologies which are that big, like an automotive chassis, which is the outer covering, or you are trying to build the automotive complete bumper of a particular car, right. So these are some bigger printers which are used. Some printers are used for a lot of aerospace applications. Then you may have heard about metal 3D printing, right. So metal 3D printing is again another technique which is currently used by big companies like NASA and aerospace companies like Lockheed Martin and whatnot, right. Metal printing is getting slowly more popular in India. I think there may be 1 or 2 printers which are in the top institutes, and maybe with the DRDOs they may be having a few, right. So metal based printing have a little bit different technology, where you have basically a metal which is being which you change into a molten stage, and then that is being deposited in different layers. So surprisingly and interestingly, we are also getting a huge 2 meter by 2 meter printer, the largest printer in the country in my lab in AIIMS. So that should be there pretty soon, and we are planning to use this printer for prototyping different human scale armors, as well as looking at ergonomic furnitures and several other body wearable equipments, and this would be one of the largest printers we are building in the country, right. So far what I have seen is typically the printers are maximum sizes like 1 meter, 1.5 meter, what is being used for research, right. So this is the first time we are trying to get a really big printer for several specifics. Then the third one is layer thickness. So this is another very important criteria. How much should be the layer thickness? So basically this determines how smooth or how nicely contoured your particular product is. So if you have a layer thickness which is really high, like a millimeter, 1 millimeter, then you will see this clear roughness or clear layers and the lines around the surface, right. But if you have a layer thickness of 0.1 millimeter, it is much more smoother and nicer, because typically a millimeter is something which is visible to the naked eye. 0.1 also maybe, but typically it goes very, very small. You will not see those undulations there, right. So then the next one is nozzle diameter. So you may think, what is the difference between layer thickness and nozzle diameter? So nozzle diameter is basically how thin am I trying to take this material out from. So basically nozzle diameter determines that how much material I want to bring out and how thin is it, and this is usually in sync with the layer thickness. So if you have a nozzle diameter of 0.4 and layer thickness of 0.1, that is very difficult to achieve. So you are sending out a lot of material, but trying to have a layer thickness which is much more smaller, that is very difficult to achieve. So typically the layer thickness and nozzle diameter would be very close. Typically the nozzle diameter would want to be a little lower than the layer thickness, because if you have a nozzle diameter of even 0.2 and you are trying to get a layer thickness of 0.1, it will be difficult to maintain, right. So 0.2 will automatically give you a 0.2 layer, right. But if you have a nozzle diameter of 0.1 and you are trying to get a layer thickness of 0.2, you can have it built like in 2 goes, or have the material flow a little bit to get it to the point that it can have 0.2 millimeters, right. So nozzle diameter, layer thicknesses are two other parameters which are important part of the 3D printing selection. The next is print speed. How quickly is your cursor? I am talking about cursor because it is very easy to relate within a mouse. So it is just like a cursor. It is basically taking the feeder and the extruder assembly, it is moving around. How quickly is it moving horizontally, right? Whenever we talk about sprint speed, we are talking about horizontal typically. So how quickly is it moving? So they can range all the way from 10 millimeters per second to all the way to 150 millimeters per second in typical FDMs. Okay, so I would like the speed to be high, right? Typically I would want my print to be finished very quickly. So why would I ever select 10 millimeters per second? That may be a pertinent question. Why not go for the highest speed and just do it? So whenever you have a high speed, the finish goes bad, right? So there needs to be a perfect sync and optimization between how much material is coming out and what speed you are moving the cursor in. If you have very little material coming out and the cursor is very quickly moving, if we will just put the material somewhere and it will not have material for a certain amount of time as it is moving, right. So the right optimization, the speed at which the material is coming out and how much material is coming out, that has to be in sync, which is known as the extrusion speed. The extrusion speed has to be almost close to the printing speed, right. If the extrusion speed is lower than the printing speed, then what will happen? You will have cavities or bubbles or holes in your model, right, because you are not able to extrude enough material and this is just going like this, it is trying to print, then you will have holes, certain places in your model does not get any material. If you have extrusion speed which is very high compared to the print speed, then in certain places you will have too much material. That is why does it have to be completely equal, that extrusion speed is equal to print speed? Not really, it has to be much more closer, right? If you are looking at a print speed of let us say 100 millimeters per second, keep the extrusion speed somewhere similar, maybe 95 or 105, that is fine, but do not keep the extrusion speed as 20, that will create a problem. Okay. So, these are several parameters which are basically which kind of determine what kind of printer you are looking at to purchase, right. And this also depends on the kind of job or product which you are trying to build. If you are trying to build a high precision medical product like a dental implant which goes inside the mouth basically, then that has to have a printer filament which is compatible, biocompatible, that has to have a high precision, because if you have rough surfaces that can cause infection and ingrowth of like several bacterias and like several diseases while this is getting together with the bone. So, there should be several considerations like in terms of like how the finish should be of this particular product, right. So, you need a high precision product for several medical products, and there are cases like in like wearable technologies like the smartwatch, you do not need a high precision product. You need a very crude design quickly made to make a prototype, and later on once the prototype is validated you can maybe give it out for injection molding, not 3D printing. Okay, that brings me to another very important aspect. 3D printing is typically a very slow process. So, if you are trying to think that I am going to set up this big manufacturing facility with 2-3 3D printers and print everything, and this will be really good for my business of this medical products, you are probably going to be surprised and taken aback, right. So, typically 3D printers are extremely slow. 150 millimeters per second is like you are looking at 1.5 centimeters per second, it is nothing, right. If you have a big print which is in the order of let us say 10 centimeters by 10 centimeters, it will take quite a bit of time, right. If you have a bigger print, even more time. Think about a print which I am trying to get from the 2 meter by 2 meter by 2 meter printer, right. So, this big printer would need a much more higher speed, much more material coming out, and maybe the speed has to be a little higher. So, 3D printing is a very slow process. It is not a process which is usually very good for mass scale manufacturing, but I will showcase an example today where we have used it for mass producing. And typically how we have done it is we have not had 2 or 3 printers, we have 35 or 40 printers, right. So, that way we have scaled it up, because every printer is taking its own sweet time to print this particular device or print this particular technology which we are trying to print, right. So, this gave you hopefully an insight into what FDM based standard 3D printing options are in the market. Now, if you look up 3D printing and you are trying to buy a 3D printer of Amazon or somewhere else, you can clearly specify your details, what you need, what is the size, what is the level of precision or speed which you require, and get the right printer for the right price, right. Otherwise, you will be just shopping around. Let us look further. So, fuse deposition modeling technique, which is one of the most standard techniques in 3D printing, has several issues in terms of quality. How do you maintain quality? See, quality we had spent quite a bit of time discussing in the previous lectures. Quality depends from product to product. What exactly are you trying to deliver? Are you trying to deliver a product where high amount of finish or smoothness in the surface is required, or are you trying to deliver a product or prototype where just something which you can see and touch and feel is what is needed? Or there could be products which needs nice assembly of certain parts, they need to be really smooth and nicely finished, right. So, that brings us to the discussion of good quality and poor quality 3D prints, right. What are good quality prints? What are some of the key technical characteristics of a good quality 3D print and technical characteristics of a poor quality 3D print? Let us take a look. So, good quality 3D prints is when you need a low layer thickness, right, low layer thickness basically means you have much more nice outer finish, right. The first point is kind of in gray, which is make build area which does not matter, right. So, this is an emphasis. Typically good quality prints are sometimes used in areas uh, which do not matter, and majorly they would be used for areas which do matter, right. So, you would want to go higher in the quality for areas which actually matter to you, and maybe you can compromise on the quality which does not matter. So, in an implant, if you have different components, you can maybe make a component which does not matter or go inside the implant, where the surface texture or the roughness, the smoothness does not matter, and you can use a low quality 3D print for that. But for the outer surface, let us say it has to be very smooth and nicely balanced, then you use a good quality 3D print, right. So, good quality 3D print is has a characteristics of low lower thickness, low layer thickness, medium high infill. What is this infill? Infill is basically how much material is inside. So, does a 3D print build this layer by layer and goes through the entire block, or does it create an outer surface, right. So, there we come to the concept of infill. So, let us take a look at this figure where we are looking at the different percentages of infill: 5%, 10%, 20%, 40%, 80%. This is how typically the layers, this is you are looking at one layer of 3D print here or a few layers of 3D print. This is how typically a layer would look like, and the infill. So, the inside is typically hollow in the prints. Like if you have a 5% infill, you have a nice outer surface, but the inside is majorly hollow, 95% is hollow, right, because you are trying to build a prototype, you do not care what is inside. So, you have used a 5% infill. Then you can have 80% infill for particular products which is nice intricate features, very complex intricate features. There you want to make sure the inside is not void and has a very high infill, right. So, infill, how much you put depends on the kind of product which you are trying to build. Is it just a showcase kind of product or something which you where you need to have internal complexities like properly defined. So, that is the story of the infill, right. Next thing is low medium print, basically is something like which is speed which is controlled. Like if you have too high of a speed, it will not be a good quality print, because there is a very high chance of slipping basically, which means that the rate at which the material is getting out, that is not the rate at which you are printing. So, there will be cavities and holes and the print quality will not be good, right. Then another aspect is low medium, this material nozzle temperature. So, if you have a nozzle temperature, nozzle is the extruder basically, which is very high, then what will happen? The material will completely melt and it will not be able to solidify very quick, right. It is just like if you boil the water too much, you will not be able to drink it very easily, it needs to really cool down, right. So, if you raise the temperature of the extruder way too much, then the filament has basically gone into the liquid phase, into a extremely flowable phase. Now, when it is being set in the layers, it is still flowing. So, the layers may go here and there, right. Typically, the idea is by the time it is finishing the layer, the entire layer should have solidified, that is the idea. Then only you can place the next layer. If the bottom layer is liquid still, you cannot place the next layer. So, when you finish a layer, it is totally solidified, then you start another layer. That is typically how 3D printing is done, right. So, the material nozzle temperature also plays a very crucial role into this. Next is presence of supports. So, before we get to the supports, let us take an example. So, let us take an example of this two prints of this particular rabbit or whatever specific animal print, model print this is. So, first print here in the front is a very poor quality print, you can say it very loud, right. The second one looks much more smooth and nice quality. So, what is the issue here? The first one has some layers which are shifting, or maybe the speed of the extruder was extremely fast, it missed out on a few layers, and the printer conditions are not accurate, like either the rate at which the material is coming out, or you have overheated the extruder. There could be so many issues which are specific to something looking bad, right, in terms of print. The last one is presence of supports or dissolve, right. So typically whenever let us take a look at the figure, second figure on the left. So whenever you are trying to build something like a pole kind of thing, right, which keeps on going up, you build it layer by layer, then all of a sudden you want to make this top of a T. Think about it, the shape T. You are trying to make that T using layer by layer. Now while you are trying to place the first layer of the top, this thing with the T, basically what happens is your layer tends to fall down because it is still not solidified and it has a tendency of falling down. It is not able to be held somewhere. It is like you are trying to lay up a bridge, right. Can you just take this bridge and lay it? You need certain foundations and certain points which you connect step by step in order to build that, right. You cannot just say I want to build this bridge from this side to this and let me just put the bridge in one go. That will never happen. So it is that bridge effect. Think of the shape T. So you are going from the bottom, you have reached the top where you have the T demarcation, like where you have the horizontal part, and there all of a sudden the layers were going like this, and here the layer has to go all the way like this, right. So that is where the layer tends to fall down and it is not able to support the top layer, and when more weight is built up, as the more layers are built, the entire model kind of shrinks or has a tendency to fall down, right. So this is an example which is shown here in this T, where this one pillar is only there and basically you have material which is kind of like looped around and it is not able to hold, right. It is not a very clean finish at the bottom, you have messed up material. And the same print, when given with multiple pillars, it is holding up very well. So typically the idea is, when you have a pillar or a support, it is known as a support or a foundation, very close to each other, maybe within a few millimeters, like 1 or 2 millimeters, then with that particular speed of the extruder, it is able to jump from one part to another, right. So it is able to keep that smooth finish as it is going layer by layer. But if you just put it on one pillar, it is going to fall down. It is like putting a bridge on a single pillar versus multiple pillar. Hopefully the idea is clear and you are seeing part of this aspect while this rabbit model is being printed. So you see this particular ears basically, where all of a sudden you are kind of printing in the air because you are going out where you do not have a foundation. You are trying to print like this, right, in the air. You have a foundation. If the foundation is like this, that it is a pyramid, it is very easy to build because the foundation is strong and then you are going pointy. But think about a reverse pyramid. Can you 3D print a reverse pyramid upside down, right? It is very difficult because every layer you move forward in the top towards the top, it is going to have a tendency of falling down, whatever material you use. It is not only with 3D printing, think about construction material also. If you start with a pyramid upside down, the layers will tend to fall down or apply a weight and kind of curve down and things like that. That is exactly what is happening with the ears of the rabbit. Like basically it is going in this direction, the printing, and it does not have a support layer, so it has a tendency of like material falling off. That is why you have a very poor finish. How is this particular case solved in the other model? Here supports have been used. Supports mean wherever you have an overhang or some kind of a thing just lying around, all of a sudden the layer shifts like this and this. Then there are multiple supports which are basically sacrificial kind of supports which are built by the 3D printing software. They have got so advanced, and then those supports can be removed later on, either by breaking them or dissolving them. Earlier there used to be dissolvable supports where you need certain chemicals to dissolve them and the supports would be of a different material. These days, to save time and cost, you have a single material only, and supports are typically structures with a which can be easily broken or taken out, trimmed off, right. So that's as far as the particular good quality 3D prints are concerned. You basically want to make sure that the supports are proper, there is a smooth finish, and you are able to properly work through the layers, right. Then you have something known as a poor quality 3D print. So poor quality 3D print is has a characteristics of high layer thickness. So if you have a very thick layer, it is typically will give a very poor finish, and it's a poor quality print. Low infill. So sometimes if you have very low infill, typically I never print with 5% infill. I would always go with 20% or above, right. 5% infill has a very high chance because the entire inside is hollow. Even if there is some layer shift or things are not able to be held while this is building up, it will give a very poor finish, or it will not be able to hold up weight in several layers and whatnot, right. So low infill is a characteristics of poor quality 3D print. Then you have print and extrusion speeds which are fairly high will also give you very poor quality 3D print. So if you have a low or medium extrusion or print speed which are in sync, typically you would get a very nice quality print, slow and steady, right. But if you have a super high moving cursor and the material is coming out and then you are constantly moving it at a very high speed, you will see some printers going at very high speed, they will give a very poor finish, right. Then wrong nozzle temperature. This is another reason for getting a poor quality print, is when the nozzle temperature is extremely high. They have to be tuned as per the material, right. If you have a particular material which is ABS or PLA, they have different temperatures at which they melt. There are set temperatures quite well known in Google, and it comes with the manual of the filament that please set this at 210 degrees Celsius, right, or 230 degrees Celsius. So now if you have put a material which melts at 230 and your temperature is just 210, it will not melt, it will not ooze out material at all, and your print will not go on, right. If you do the reverse, if you put 230 for a 210 melting material, it will start coming out flowing like like water basically, right. Then you do not have control on the layers, then many of the layers will have cavities, right. And the last part why you would have poor quality 3D print is not having any supports for any kind of overhangs like the T or something which is all of a sudden shifting the cursor to the thin air where there is no support, then the printing quality would be bad. And all the results of the poor printing quality aspects would basically give you something very similar to this rabbit model, which is poor quality versus the other one which is really good quality, right. So these are some aspects of the fuse deposition modeling FDM based 3D printing. Let us look at a few other print quality issues which have to be looked into, because I think 3D printing is one of the most common manufacturing techniques which we use for building several medical products and wearable products. That is why I am spending a good bit of time trying to explain what 3D printing is and what are some of the things you have to be careful about, right. So there could be several print quality issues which may come with your 3D printer. So it is not a plug and play device as you may think, like a regular printer. So regular printer, what happens, you click on a Word document or PDF document, it keeps on giving you the same consistency of the print every time, and unless the cartridge has run out of ink or something like that, right. That is a separate issue. But typically otherwise till 600 or 700 prints, whatever the cartridge or printer is rated for, you will have very consistent prints. But in 3D printing the idea is not very similar. You cannot think let me buy a 3D printer, and I am an entrepreneur who have no engineering knowledge, and I am trying to buy a 3D printer to prototype, and then my colleagues in my particular entrepreneurial venture are basically trying to get 10 prototypes of this because they are really excited to use this as a marketing tool, and they want to roll out to different cities in India to showcase this to several funding agencies or VCs or whatnot. And all of a sudden you see these 10 prototypes are not the same, and after the 4th or 5th prototype things are not looking very well, right. Like it's weird lines are showing up, and then it's very poor quality. So that's typically the issue with the FDM kind of 3D printers. You need a skilled manpower or somebody who is trained, or train yourself. There are a lot of YouTube videos to train yourself with the quality issues. I'll explain a few here which are important. So you should have an eye on if a particular line in the 3D printing is looking like this, or there is a particular quality, like I can tell off my head this is probably what the issue is. I have to adjust the nozzle temperature or nozzle speed. So this is typically a very in-depth understanding, and typically with additive manufacturing technologies, it's a course in itself, right? Like people do their complete degrees in additive manufacturing. So we are just taking a snapshot of that. But the caveat here is 3D printing is not that easy what you would think it to be. Buying a 3D printer is very easy, but sometimes using it or maintaining the same quality is very challenging, right? So let's take a look at some of the print quality issues which can be faced. So one of the very common print quality issue is a bed leveling issue. So what's a bed leveling issue? So you are basically having this bed or the block on which your 3D printing is happening, right? Like your particular product is getting built layer by layer. So you have this wooden bed or a glass bed or whatever bed you have. Many a times this bed is not exactly leveled how it should be. It's a little tilted, right? Typically happens with printer which has moving beds. If you have a constantly fixed bed, this is less likely to happen, but with printers which have moving bed, where bed is deciding the z axis or moving the entire print along the z axis, that is where basically this bed is sitting on 4 screws on the sides, right. Very often than not, those screws are all kind of synced together, but have different motors playing with it, basically moving them. So they can get a little off, and even if a few degrees, 5 to 10 degrees, can cause huge amount of harm to your prints. So let's take a look at the bed leveling issue. On the left, you are seeing a print where you are seeing some layers on the left. The outside layers are okay. On the left, you see layers where they are not very smooth, they are much more rough. Then you have layers which look pretty good and consistent in between. So typically layers where you have too roughness, so that means too far from the nozzle. So these layers were a little far from the nozzle. Why did it happen? So your nozzle is coming like that, and this is your bed, and this is where it is printing. Now your bed is kind of tilted like this. Now the nozzle is able to touch here, but nozzle is not able to touch here, right. That is where the problem starts. So this is probably drastic what I am showing, too much of scaled up image, but let us say the nozzle is just able to touch here or just touch here. So the amount of material it will properly smoothen out or send out like here or deposit is not the same as here. That is why you have too far from the nozzle case where you have rough edges. This is one of the common reasons, right. Then you have another one where it is too close. Then the complete print is damaged, like in that layer is not existing. So think about this nozzle again. This is a normal bed, and this is this nozzle. It's going like this if it is all leveled, and this bed has now moved like this because I have not taken care of the bed leveling for a while. So here I get a too far from the nozzle kind of system. Here it is too close to the nozzle. The nozzle was supposed to be like this, right, be able to move here, but it is not able to move here because it is hitting the bed. So that is where I am that bed is blocking the extrusion of the material and the flow of the material. So it is hitting to the nozzle like this, and it is blocking the material to come out. That is where I have a too close kind of scenario where you will have layers which are missing, right. So this one picture on the left gives a very nice idea of bed leveling issue where you have a pretty good condition, then you have too far from the nozzle and too close, right. Let us look next. There is another issue where your print would look like it has curved in, right. There is it was supposed to be a completely flat print, but it has somehow curved a little bit up. that is again a very problematic and shabby looking print, right. So, what is exactly the case? There is a science behind it, and the rightmost picture actually explains it. So, you basically have typically a bed which is heated, right. So, the bottom bed can in majority of the printers do not have a heating, but typically there are some heaters which are put along with that bed. It is known as a heated bed technology. Majority of the good printers have it. Heated bed just makes sure that when you are placing the first few layers, all these layers are sticking in well with the bed. This amount of heating is doing that extra. This is not at 210 or 230 degrees, a little lower than that, but making sure there is some slight melting on the edges and the layer sticks well. Because if you do not have the bottom layer sticking very well with the bed, then sometimes if you have bed leveling issues and other things, this entire extruder will hit the model and it will bump out, right. It will just go out of the bed, and there can be relative motion between the particular model which you are trying to build and the bed. We do not want any relative motion, we need this fixture to be very constant, right. So, sometimes this majority of the times actually, so you would want to use a heated bed. Usually it would cost you a little extra to have a heated bed, but there is this heating of the bed, right. So, typically what happens is this is known as warping, where you have the 3D printed model kind of curving in, where the bed temperature is a little higher, right. Bed temperature is a little too high, set little too high, that it is kind of melting or molding, and it is causing this particular uneven expansion or uneven. So, typically heating will cause an expansion, right. It is an uneven expansion that the bottom layers are getting expanded later on, not in the initial part. So, initial part it is very good. Now, let us say you are 10 layers up, right. So, the up layer has no access to the heat of the bed, right, only the first 1 or 2 layers is getting heated by the bed, everything is like kind of just getting placed. So, the bottom layer is heated the most, that is going through some expansion, the layer above it has a little bit lesser expansion, layer above it little bit lesser expansion, 10th layer probably no expansion. So, the entire thing just wraps into this uneven expansion, and this entire model just goes like this. This gives a very shabby kind of outline. Hopefully, this is clear. Everything else is going in the same, the printing speed is okay, the extrusion is okay. It is because of the bed temperature which is maintained, the warping is happening, right. The next example or issue is filament break issue. So, filament break issue is very common. You are seeing the example of a kind of a semi miniature model of a dinosaur, and basically you are looking at a completely messed up dinosaur, right. So, what is the issue here? Why was the second case happening? And you would find this very often with your printers, right. This is typically when you have either too much of material which is dispensed, or there could be cases where your nozzle is not getting out material, right. The issue could be either due to your extrusion temperature or the speed at which the extrusion is happening, and in majority of the cases because your feeder is faulty. The feeder is not able to maintain the same extrusion speed, or the feed flow of the not the flow, specifically the feeding of the filament is not at the correct speed where it should be, and it is either being underfed, where basically it is coming out at a much more slower pace and few layers are going in the air, there is nothing in there, and the extruder is still moving around. Okay, so taking a step back now, how does this extruder actually moves? Like, what drives it? What tells it that this is the layers? So, this is known as a G code basically. This is a code which is fed with a 3D printer. This is typically, majority of the codes are like open source, and they are typically generated when you place a model, 3D model, into a software which is a 3D segmentation software or 3D printing based software, like Cura is an example. If you look up Cura, if you place a model, it will quickly convert that model into a G code. G code is nothing but it is a set of coordinates. It basically tells to the extruder or the motors that please move from 100 to let us say 120 or something like that, and just keep on going, right. So, typically 0, the last one is a z axis x y z. So, let us say 100 to you now go to where is this that is your home position, and you go from there to 120, or let us say 130 or 230, whatever this path of the printer is. It does not have to always go in a certain direction, it can go in different zigzags, but it has to be having the 0 as the x, z as the constant, and then the 0 keeps on going up. Let us say then 211, 221, 231, something like this. So, this is what the G code does. G code has this entire set of coordinates which this model has been divided into. So, the computer based software, which is this 3D printing software, basically takes care or forms this G code based on any model which you put. So, a particular device which you are trying to print, like if you have a dental implant which you are trying to print, it will have a different G code than if you are trying to print another dental implant of a different side, and as opposed to if you are trying to print let us say a smartwatch casing, right, it is very different. So, the G code basically will tell the cursor where to move, that you move from here to here, then here to here, here to here, now you have moved 100 places, and now you shift the layer, keep on moving in the same direction, and in certain cases they will shift the movement. So, that is what the G code does, right. So, many a times you have the filament break issue where either the filament is not fed right, or due to too much of extension and flexing, the filament has completely broken down. So, now it is not feeding. Typically happens when 3D printing does not have a supervisor. So, many a times this happened to us, like when we have left the 3D printing to happen overnight, and that we will come in the morning and everything will be done, right. It is a 8-hour print, and we leave at 12, and then think of at 8 AM we will get the print, and at 8 AM this is what we see, the filament has broken somewhere and the print is not proper. So, it is a waste of your time. So, it is a good idea to keep an eye on the printing and visit it like from time to time. Another issue is the layer shift issue. Layer shift issue typically happens when the extruder hits on a particular layer and kind of moves this entirely. It is also sometimes a side effect of the bed leveling issue. Sometimes you will have the layer shift, but many a times and majority of the times it is a coding issue. So, in the G code, something has gone wrong in that particular layer, that the coordinates were not put in right. Many a times G codes are faulty, right. So, layer shift issue typically we have seen due to the issues with G code, but majority of the times they also do happen due to the bed leveling issues and other stuff, right. So, these are the list of some of the print quality issues which you will encounter on a day to day basis if you are trying to build a 3D printed product, right. Let us go further. Let us talk about the next technology in the 3D printing, which is very popular. This is known as stereolithography or SLA. So, SLA basically uses a liquid photoreactive resin, much more difficult to handle. Earlier you had everything which is dry and solids, now you are dealing with something which is liquid, right. SLA printers are much more expensive. You will usually find a good SLA printer from 50,000 or 60,000 rupees plus, and they can go all the way up to crores, and sometimes some of the SLA printers can even go higher, right. So, this SLA printing typically has a liquid, and it prints basically in the different settings. So, it is a bottoms up and top down approach, like so. What you have in FDM printing is basically you go from down to top. So, from bottom to top is how you go. In SLA you go a little differently, you go from top to bottom, right. So, basically what happens, you have this liquid and you have a laser beam traces one layer on the surface of the resin. The laser light cures that particular surface of the resin and solidifies the part where the laser hits it, right. Then the platform kind of goes down. So, the end product is very similar, it is kind of building from the bottom only, but the process is a little upside down, right. So, earlier what you would do typically is you are building a layer and you are going from layer to layer up like this. Here the entire system or your model is coming down as you in the bath of liquid. So, there is a platform, and within this, right now the platform is at the top of the liquid, there is this laser, it cures it, first layer done, platform goes down, next layer done, platform goes down further, next layer done, 1 millimeter or maybe 0.1 millimeters, and finally you get a nice and finished product because this liquidy material and the laser technology is extremely high precision. But what you do have is it requires a lot of maintenance, lot of time and lot of post processing, right. So, let us look at the principle here for a second. You are here looking at the platform and piston. I am looking at the figure on the bottom, and this is the YouTube link for this. You can look up this SLA 3D printing, or just search up SLA 3D printing, you will see what it looks like. So, you have this platform and piston, then basically you have this liquid resin bath, and on top of it, at the very top the laser is kind of shooting and creating the layers, and basically you are coming down with this particular product. Recently they have come up with some SLA based technology which is fairly fast, because usually the laser curing would be taking a lot more time. So, they are fairly fast, they can print flexible materials also, there are a lot of choices of materials very similar to FDM, but the finish and the quality is excellent, right. Typically I have seen the finish, we have an SLA printer in our lab too, it is an heaven and earth difference. If you actually look at the product from an FDM versus SLA, it can give very fine details. So, where to use an SLA, where to use an FDM? So, if you are looking at dental implants or some form of implant prototypes, you might want to use a SLA based printing, right. But having said SLA, you need quite a bit of post processing, like it has to be curing, and there are some liquid baths on which your product has to be placed to make sure the exteriors are looking nice and everything like that. Any supports are removed if there are any form of supports. Here in this figure you are looking at bunch of supports. So, basically the model is at the very bottom, and the other ones are basically supports. So, these supports have to be dissolved. So, it is very time consuming, but you get a very high precision product. But if you are trying to just showcase something very quickly, which is a crude product, and it does not matter how it really looks like from outside, it is just the functionality or feature what you are trying to explain, go for FDM. Okay. So, SLA is not very time effective or cost effective, it is a little expensive and more time consuming. FDM is much more quicker, but SLA quality is much more better. So, these are the two key techniques of 3D printing. Further into the SLA technique, there are a few 3D printer variants. So, how do you decide among the SLA what kind of printer to be selected, right? Do I go for a 70,000 printer or 20 lakh printer, what exactly? You look out in the printers in the market, they will give you anything, right. So, what is the correct printer specifications to mention? So, do not get into the price both for FDM and SLA, get into the specs. Whatever specs can be offered correctly, that will define what are you using the correct manufacturing technique for building your product. If you are putting the wrong specs and a lot of money, that is not going to help, right. You can put 20 lakhs for a printer which is probably worth 5 lakhs, and without the right specs that will not work, right. So, look for the specs, that should be the key word or key focus rather than the price, right. So, that is one of my key suggestion here. So, let us look at some of the features here. So, one is high resolution and accuracy. So, SLAs typically differ from FDM. Let us take a look at the two prints here on the very top, right. So, you can look at a laser SLA based print versus an FDM based print, very crude looking FDM print, very nice and cool looking SLA print, heaven and earth difference, right. So, typically you have a better solution for complex jigs, highly accurate tooling and molds, general and DIY. These are typically the avenues in which you will be using an SLA. FDM is better for large and simple parts. something which is very simple like a block, or some lock and key mechanism, or you are trying to show some nice implant or nice prototype, right, at a higher scale. Later on it will be built at a much more lower scale, but you have enlarged the scale and you want to just showcase it to some investors or some possible customers. So these are nice, typically where you use an FDM. More choice of materials, right. So typically wide range of compositions, hard to soft is what you find for SLA printing. FDM you have very limited choice of materials. SLA has much more wider choice of materials. So with this I would like to thank you. This is all for the session. Hopefully you have learned something. We will see you next time for the next class, right. Thank you.